Just an overview of the work we've done. I know that we've talked about this project already, and in particular, Guy, Jack, Sasha, Rachel, and Natasha, who's here, are all working on this project, as well as being supervised by Simon, Greg Stiller, John Easy, and Sharon Atkins. So, it's already been introduced, but basically we're looking at signature whistles to use them as a mark effectively, to look at occurrence, to recapture animals over time and space, and then somewhere in the future to use signature whistles to calculate density of dolphins within a population. Now, our two populations that we're working on are the inshore bottlenose dolphin population in Namibia, and also the endangered humpback dolphin population around the coast of South Africa. So in Namibia we've got around 100 or so very, very coastally located bottlenose dolphins, as well as the humpback dolphins around South Africa. We think we've got less than 500 of them, and it's probably split into two subpopulations as well. Traditionally, as many of you will know, to generate abundance estimates or look at ranging patterns of dolphins, we would use high-quality photographs of their dorsal fins, which are individually distinctive, and then we would recapture dolphins over time and space using photographic methods. But there are some logistical difficulties in doing this, particularly with populations which are very, very coastal, small populations and those which range over a large area. For this reason, signature whistles have been proposed as a potential solution, and using them in the same sort of mark recapture framework. So, although this was proposed in sort of 2005 by Terry et al., really it's only in the last 2 or 3 years that there's been strides in terms of developing this methodology. So just a reminder, signature whistles are learned individually distinctive whistles in the dolphin's repertoire that broadcast the identity of the whistle owner. So they're learned in year 1, they are individually distinctive, so there's most similar, we've got human vocabularies that are names, and they're used in recognition as a contact call and in referential communication. And they're stable over time, and that's really important in a mark recapture framework. So here at the top you've got Zulu from 2010, and then Zulu from 2020. You've got Kitiwe from 2020, and Kitiwe from 2020. These are from the captive population through in Durban in South Africa. So just a note, in 2013, Tiago Marquez has a great review of estimating animal population density using passive acoustics. And although there have been major developments in conducting ASCR, we're actually more in the framework of the mark recapture and camera traps. So we're looking at capturing animals over large areas and through their unique identifiers, not trying to calculate densities from cues of animals, which has been done previously with frogs, for example. So first we have to identify our dolphins, and historically, and particularly in Sarasota Bay, dolphins have been isolated. They often call out their signature whistle when they're stressed and in a situation where they want to maintain contact with one another. And then from those recordings, the populations where this has been undertaken have been able to assign a signature whistle to the individual, and then also record those individuals when they are freely interacting with one another. Ideally, in a wild population where we didn't want to capture the animals, we might want to tag them, but again, this is quite costly and logistically quite difficult. And so there's another approach using about analysis, because basically, as Sam always says when he does this talk, dolphins basically swim around the sea just saying their own name. And so if you look at these bouts of stereotyped whistles, more often than not, it's an individual producing their signature whistle as they move around the environment, and particularly for mums and calves. So we can identify them in long-term recordings using this bout analysis approach. And as we probably all know, there's different ways of classifying the repertoires. We can also use automatic categorization as well as visual categorization. With the larger data sets, we've used a machine learning approach called artwork, which combines a neural network with some dynamic time warping. And this is what it would look like. So basically, you trace the contour of the whistle, and it's an unsupervised neural network. So basically, it's taking the data and it's comparing each whistle contour to the next, without me saying anything about how many categories there should be. And then from those data, you can look at the temporal patterning of the production of the same whistle contours. Okay, so we've used this approach for identifying likely signature whistles in common bottlenose dolphins around Africa, in common dolphins, and also in Indian Ocean bottlenose dolphins. So the next step is then to say, well, can we identify and recapture signature whistles over time and space? And in 2014, we started trialing this using base data from focal follows, and we were able to document 28 signature whistles from our population in Namibia, of which 23 were recaptured over time, over different years, and 4 were recaptured over a spatial distance of 450 kilometers. So how many hydrophones, though, do you need in one location? So if you want to conduct market capture over space and time, and if you want to then put your hydrophones out into the environment without you being on a small boat and just leave them for many months at a time, how many hydrophones would you need in one location? So do you need to cluster those hydrophones, or would one suffice? And Jack looked into this question, and he found that on a fine scale, actually, a single sensor will suffice, and that as long as you place it in the optimal position, which you kind of need to have a little bit of information on, the capture probability of signature whistles is the same for one hydrophone as it is for 3. And what duty cycle to use? Well, Jack also looked at this, and we know that dolphins are very fast-moving, and they're often producing these signatures in bouts, which occur over quite a short time frame. And so actually we found that the shorter duty cycles are better, with about a 10-minute on and a 5-minute off duty cycle. And that obviously has relevance for the amount of memory and the battery life of the recorders. Okay, which deployment sites to use? Well, in Namibia, we also put the hydrophones across, we had 4 hydrophones, we put them across the bay in a core use site, but we were actually conducting this work as part of monitoring coincidental and coastal construction. And what we found was that there was quite a lot of spatial heterogeneity in terms of capture events. So in some areas, we were getting a lot of dolphin presence identified through both echolocation and whistles in the recordings, and in others, much less. And then there was also instances, which is quite useful to know, where animals were moving through a particular area. We knew they were there because we detected echolocation, but we didn't identify any whistles at all. So how long do we monitor for? Well, we looked at one of the high-use sites, and over 125 recording days, we were able to capture 53 signature whistles, and basically after 4 months, the discovery rate flattened off. So we would say that here we would need at least 4 months, but we were recording for 6 months in this small population. And can we capture the total population? So one of the ideas would be if we could sense the population using this method. But in effect, we know that there's a lot of difference in terms of the vocal production of bottlenose dolphins linked to context and also arousal. And this is some of the work that Rachel Robert's done, gaining captivity. And this is across the x-axis, we've got the time of the day. And we can see that basically in the early morning, often when the lights is coming up, but also the trainers are arriving and food is being prepared, you get a massive increase in the signature whistle production rate. We can draw some linkages between captive dolphins and wild dolphins, but sometimes, as well, we do often need to remember that captive dolphins are quite a different beast of animal. But they do show individual variation in the production of signature whistles as well, and this is something we also see in the wild. So along the bottom here you've got the productions of the different whistles in the captive colony, and you can see that certain individuals are much more vocally active than others. And this is again what we see in the wild as well. So you can divide this into your chatty and your chilled animals, but in general, for each encounter, you may have just 1 or 2 repeats of a signature whistle, or you might have up to 50 repeats. So, does our potential method work, and does it show promise? Well, we have been able to conduct mark recapture of signature whistles, and we've been able to generate estimates which are very similar to the photo identification estimates in Namibia over a similar time period, so that was actually remarkably rewarding to see. But in Namibia we've just got one population of dolphins that whistle and occur in the coastal waters, and that's our common bottlenose dolphins. So what happens when we try and transfer this to other species or other populations? So our humpback dolphins, they share both an acoustic space and a physical space with other dolphin species along the coast of South Africa. And in fact, they also share very close quarters. This is actually a common dolphin calf with a humpback dolphin female. And we're not quite sure how that arose, but just to say that issues with mixed species groups do occur, and that complicates your analyses and your detections if you're looking to try and classify a particular encounter at a species level. The other thing that's quite complicated is that you may be recording or next to or close to a group of humpback dolphins, collecting information which we hope to use for the verification of the species classifier, and your animals that you're with are quiet, but you're actually detecting either another group or another species even from several kilometers away. And Vincent Yannick in 2020 hypothesized that you can actually detect whistle vocalizations in absolutely pristine conditions up to 20 kilometers. At least 2 or 3 kilometers, and at least without visual sighting. So that does mean that you know, as much as you try your best to verify your data and get single species groups, you can still come back to the office and see that you've got, say, common dolphins in your recordings. And the other thing I noted is that they share acoustic space. So our humpback dolphins, for example, seem to be quite unusual in that they are putting more energy into the second harmonic there, and also they sort of range in frequency as massive, so they have fairly low frequency whistles and then occasionally go very, very high. And we think that is related to mating activities, but that just means that it's an extra complicated step in terms of your species classifiers, because you've got a wide range of frequencies that the dolphins are calling at. They are very highly cryptic, and you have these differences between species in terms of their ecology, and occasionally, you know, despite your best efforts and almost killing yourself trying to record these animals, they are absolutely silent. And that's because with humpback dolphins, for example, their defense mechanism is to be hidden away in the surf zone, away from any potential dangers. And we also see notable geographic variation in whistle behaviour, which further complicates, so you can't translate a species classifier easily from one geographical region to another and expect it to work perfectly. We see, for example, disconnected multi-loops in humpback dolphins, which become much more difficult to identify the whistles because you've got these breaks in the whistle contours. So you can't, for example, use that arc walk method that I showed you earlier easily, because your contours are broken up in periods of silence. And you do need to have some background information then on the whistle repertoire of your population. We also have different levels of individual distinctiveness between populations. So, for example, this is the Mozambique bottlenose dolphins that Rachel's working on, and what you can see here is that almost all of these whistles have a signature which is of an upswept nature, and it's not very distinctive between different animals. And you can see on the far side there that that's the result of conducting classification using Artwalk, and it's a so basically, although individuals in this study had whistle stability over time, when we tried to put them into groups that were consistent, we just couldn't do it. It's possible, or even likely, that the dolphins can tell the difference between each other using subtle acoustic cues in these calls, but to the best of our visual and automated methods, we really struggle. Okay, so in summary, small coastal populations are hard to study, and you know, we're trying these new approaches which provide new ecological insight and very novel data, which is important for small and endangered populations per se, but it hasn't been an easy road, and it requires rigorous testing, good knowledge of your studied species and population, and there has been no quick answers in terms of market capture and density estimation using signatures.